So now yesterday I was just wondering how do I start this topic of overspray application, because this is a very new concept. People who are closely associated with, they know what is happening. But then today morning I heard the keynote speaker, and then afternoon we had this session for innovations for the future. And I think you all are aware that this happens to be one of the innovations for the future. It's a disruptive technology. There's a lot going on. There's a lot to be covered also. But if you don't do this, or if you don't innovate and try to get in the future, like you heard in the morning, the automotive industry will not be relevant anymore. So they have to innovate. So let's just talk about what this is about. In a basic term, when I say overspray free, you heard already, I think John mentioning that it is nothing but digital printing. It really is digital printing. The only difference is that instead of ink, you're using paint on a car body. So that becomes equally challenging, because painting ink is very easy compared to paint with 35 microns, no drips, no sags. So what we are talking about here is digital printing using paint on a car body. So the moment you say digital printing, car body, thick paint, sag control agents or the sag control resins or the additives become very obvious, because you need that sag control over here. And so sag control becomes very obvious and people use that. But what is not very obvious is the rheology modifiers. And hopefully after this presentation, you'll realize that even the rheology modifiers have a role to play over here. And there is a synergy between them and the sag control agents. And hopefully by the end of this, you'll realize how to use them effectively in your overspray applications. So before I start the topic, I would just like to first thank two external partners. One is Dur, because without their help and without their guidance, we would not have made this progress, because this was totally new technology. It is not like conventional spraying. It is a distributed technology. And so we had to have a strong partner like Dur, who's already working on these applications. And so they are of immense help to us. The second external partner we would like to thank is Allnex, because I told you, sag control agent is something which is very obvious. We know that it's going to be required. And that is where, Allnex was of great help to us. They helped us on our journey on trying to try different solutions and all this. So getting back to this overspray application technology, like I told you, 3 years back when we were starting this, there was only one OEM line who had sort of commercialized this. It was a waterborne base coat technology with a conventional clear coat on it. That is the integrated process, the one which you see in the faint corner over here. But today, there are almost 6 lines who are almost commercialized or in the midst of commercializing. Most of them happen to be a waterborne base coat clear coat technology. But if you heard today's discussions, if you want to really innovate and you want to, be a differentiator in the market, you need to have different technologies. You need to have technologies that are shorter footprints, because waterborne base coat clear coat, you need a base coat booth, you need an IR zone, then it has to again come back to the clear coat zone. So it adds to your complexity, right? It increases your manufacturing footprint. And that can indirectly increase your CO2 footprint and your cost. So when it comes to this technology, and when we start working on this, like I told you, though it was established, the challenge given to us was, don't look at that, because that is something people are already doing it. They're already commercializing. If you really want to make a difference, focus on monocoats. And you can see the challenges given over here. Because why monocoats? Because like I explained to you, you're all from the industry. Monocoat has a shorter footprint, right? You just need a monocoat booth, goes to the oven. You don't need all these things. Repair becomes very easy. And it all translates to cost, CO2 footprint, process innovations, everything. So monocoat happens over there, right? But then there are challenges involved in this, because when you talk about monocoats versus a base coat, clear coat, these are the challenges given to you. When you say base coat, since you're all from the coating industry, base coats are inherently designed to set very fast. So the base coat can set very fast. You don't have to worry about sagging. And the clear coat, subsequently, when you apply clear coat, that takes off your appearance. But when you come to monocoat, that's a different beast altogether, because monocoat now has to behave like a base coat, so that it has to set very fast, no sags, no drips at all. But at the same time, it has to flow also like a clear coat, because you need the appearance. Because when you say monocoat, so the challenges given to us was, we need a monocoat. We need a 45 microns minimum on the vertical horizontals, minimum 30 on the horizontal verticals, but it has to be a single pass application. And it has to be a single pass application, a single paint doing the job of top coat and horizontals and verticals. And when you say verticals, they're talking about 90 degrees verticals, because you have to have that flexibility. 90 degrees vertical is the door area, right? If I can't put those bands and stripes on the vertical, 90 degrees is of no use. So the challenge given to us was, go for a monocoat, single layer, single paint doing the job of horizontal, vertical, at the same time, get all these properties, right? So like I told you, this was very, very difficult to think about, because when you realize how this machine operates, you'll realize how difficult this was. So like I told you, when we started this, Dur was a partner, because we didn't have this applicator, and it's not like a conventional applicator. So we worked with Dur. And before we started the project, this was the slide that they shared with us, what you see over here. Because when you talk about a monocoat, traditional monocoat in the automotive industry, it has a Newtonian flow. If you look at this, this is like this, but Newtonian flow will be almost straight. That is a traditional monocoat. But what Dur told us that even if you are developing a monocoat for this technology, it has to have this sort of profile. The one which is green ticked, if it is very high, it's not good for flow leveling. If it's very low, it's not good for sagging. So it has to be like this. What you see for a traditional waterborne technologies, a rheological. So this was the guideline they had given to us that the paint should behave like this. So now it's very clear that the paint has to have a non-Newtonian flow, a monocoat technology, right? It cannot be like your traditional Newtonian flow for a monocoat technology. It has to be like this. And so when you talk about a rheological flow, like I told you, SCA comes to your mind immediately because you have to build a thixotropy, right? And so we screened a lot of SCA reagents and additives also. Out of all those that we screened, we found this SCS from Molex to be the best because you could play with it. You could take the thixotropy up and down, and it had no adverse impact on the appearance. Whereas the other thixotropic agents, unfortunately, what we tested, when you're trying to play with it, go up and down, it was having adverse impact on the appearance. So what we did was we first shortlisted SCA. So that was a critical part of the formulations. Then comes the second part, because if you just use SCA, what happens? We'll go through the slides, we'll realize what happens if you just use SCA, but then you have to have rheology modified additives, right? And normally, any paint formulation has a modifier because you need to have flow leveling, right? And the conventional ones that you use, they are again Newtonian. You will see a straight line. All the additives that you use, silicon additives, low molecular ester additives, they all have straight line, right? So what we wanted over here was something else. We didn't want to have that. And fortunately, in the Eastman portfolio, we have our own CABs, the heritage cellulose ester, butyl esters. If you use them, you will realize these additives do not have a straight line. They are flow additives, they help in flow leveling, but they have a real, almost non-Newtonian flow. I'll come to those slides separately. So what happened was, we decided, okay, let's start with these two, because these are critical. Let's start with the SCA, let's start with the RCA resin. Okay, if you look at this, so the first part that we are trying to do was, now we know these two happen, we need to use them. Let us see what happens if you use them individually before we start blending them. We use them individually. So, we just made a paint. We just made a paint with SCA alone, the sag control agent. Like expected, you can see the red line. It was like this. The SCA alone. It was on the higher side. It was very good for sagging. You see the panel, there is no sagging. But what happened was you can see the peeliness, right? It looks very bad for automotive appearance. We made pure SCA, we made a pure RCA paint also, just RCA, no solar SCA, nothing in it. You see that you got this green line. Very good for flow, but absolutely bad for sagging. So the idea was just to check that, what happens if you do the two things individually. Second thing, like earlier, before we even started formulating the paint, we wanted to see how this applicator behaves because this is a different applicator. It is not like a traditional applicator. So we took a conventional monocoat paint, added a little bit of extra SCA, a little bit of RCA to the formula, and we did just one first trial just to see how this behaves. This was the result. So if you look at it, the flow leveling is pretty good, on this panel, but the sagging is still bad. Because, I told you we are targeting 25 microns on a 90-degree vertical. So this is a vertical panel at 90 degrees. This was very bad. But again, this was just a formula just to validate how this machine operates. What does this machine do? And so these are the learnings for the machine. What we learned from the machine is that this machine is literally zero overspray. There is no automation. That's why they call it overspray application. There is zero. So it's virtually like you're pouring paint on the panel. If you've got a shower head, you're turning on the tap. This is exactly like that. It's like a shower head and zero automation. So now imagine the challenge. When I said that verticals, 90-degree applications, we are pouring paint, it should not sag, but it should flow also. So this is what it was like this. So that was the challenge we had. So then we realized, okay, if you have to do this, it has to be a mixture of these two, right? It has to be a mixture of RC and SCA because individually, none of them are working. We need to have blend. So we carried out a design of experiments in our lab. So what we did is we took different grades of SCA, different grades of solars, different ratios. I'll not walk you through all the exercise. But what you show over here is a simple DOE. A 2K factorial experiments. We tried this SCA at different thixotropic index, RCA with different grades. And obviously, when you do a DOE of this nature, you end up with 16 experiments. If you duplicate, almost 32 experiments. Now, we can't take all the experiments to the line for trials at Dur. So what we did was, we used a proxy test method. Because I told you, this is zero overspray. Even if you try to use a conventional gun in the lab, you will have to have some pressure to optimize it because you're not going to spray otherwise. So what we thought, okay, if it's zero overspray, let's just take a drawdown so that there won't be any shear, there won't be any automation. So what you see is the lender paper. We took a drawdown on lender paper, and we are trying to do both, horizontal to see the appearance, vertical to see the sagging. And so we use the 16 experiments for screening by this method. That we're looking at those experiments that had a good flow leveling on the horizontals and which had a decent sag till 45, 50 microns, there was no sagging. So we chose those experiments. And those are the experiments, we took them to the line on the door. Because first trial that we did, that was just a rough formula with just a little bit of SCA, a little bit of RCA. But this was a formula that we use a DOE and we try to optimize it, with this experiments. And you can see the results over here. Right, when you do this, obviously we did an experiment on the panel side also, application side. We varied the flow rates, we varied the tip speed, velocity, we tried a lot of things. But what I'm showing you here is the end results. So can you see this? From here to here. Remember this trial, how bad the sagging is over here. Now look at the same results. This is a vertical panel, 90-degree angle. Very good for sag. So this was on the lab applicator, XYZ applicator. And like I told you, this was after a series of experiments in optimizing the SCA dose, the RCA dose, the application parameters, we got this result. So we are very happy that, okay, we almost solved the problem. Then we went to the actual applicator because, when you're doing screening, you start with the lab applicator. This is the applicator that really customers are using on the line. They call it EcoJet Pro. We went to EcoJet Pro. You can see what happened. The horizontals are pretty good, no, not very bad, but the verticals absolutely pathetic. So it's like again going back to square one. The lab level, you had a very good result. What happened over here? And that is where we realized that there are some different nuances in the pro and the lab applicator, because the lab applicator, they use it more for screening your raw materials. Like I told you, when you're starting the experiments and you're having 32 experiments to screen out, you can't use the pro, because pro you need almost half-gallon paint for doing a simple trial. If you have to make half-gallon for 32 experiments, you can imagine how much raw material you're going to waste. So the lab applicator is good enough for screening raw materials and coming with a baseline formulation, or at least getting a guideline, what your thixotropy should look like, what your flow leveling should look like. That was good enough. But what happened was, when we did this, we got a completely different results. And that is when we started to try to understand, what is the difference between the lab and this pro applicator? And there are some basic concepts. One is, I will not get into too much technical details because Dhur is more expert, they can explain to you. But what we realize is here is that in that experiment, a lab, you are able to control your flow rate from 1 bar to 9 bars. Because you could increase it, they had a knob for controlling the flow rate also. So you could play with the flow rate, you could play with the pressure, you could play with viscosity. When you come to this applicator, now the difference is that, you have got at least like a shower head, right? And you got all these nozzles. All these nozzles now have got an individual, valve to close or open them. And so what happens with this applicator now, you can't operate at that high pressure. 4 pressure is max, because if you go to beyond 4, you may break all these valves. You may damage them. So you can't go beyond that. But when we did that experiment, we were at 9 bars. When we were doing the lab, we are operating at 9 bars. But here, at 4 bars, the machines are tripping. So what happens? Viscosity, same. You have to operate at 90 CPS. You cannot spray at 120 CPS on this particular machines. So these are the learnings we got. But one thing what we learned in this, the thing is that, okay, this was operating at a lower conditions compared to the lab applicator. The pressure was low, flow rate was low, pressure was and you could not control the viscosity the way you wanted to do in the earlier trials. But what was interesting was this part. Because we'll show that, we'll come to the analytical part of it, that what progress we made from, you remember the first trial where we had very bad sagging to the trial we showed you where the sagging had improved, was because of this. We are optimizing the Rheological all the time. So once we realized that this Rheological flow was very good for that high pressure, high applicator of a lab application. But when it came to the pro, it was not good enough. So the only thing we had to do was raise that thixotropy index, because that thixotropy index was good for a particular application parameters, not for this application parameter. So what we that was our hypothesis that we used. And so that is what we started with. So we went back to our drawing board again. Okay, now when you talk about rheology, we talk about stress, how do we quantify it? Just to understand whether you are on the right track or the wrong track. So we use two analytical test methods. One is rheology, obviously, because I told you the curve is very important, and the other is yield stress. So remember the chart I showed you, or the one which BSF shared with us? This one, that if you are very high, it's bad for flow. You'll get orange peel. If you are very low, it's bad for sagging. You need to have this sort of curve, right? The one in the middle, not very high, not very low, but here. And so we had a paint which we had tried first, right, which was very bad, suboptimized paint. We had a paint, which recently we tried for our lab. We had a good results on horizontal vertical, but when you took it to pro, it was very bad for pro. So we tried to adjust those paints. So this is what you see. This is the initial sample, the first thing which we tried, which is very low. Obviously, this is going to sag, and that's what happened. Then, we had this trial 2, the one with only this, and you see this is optimized trial. So we tried to optimize this Rheological, this blue line. This is what we are targeting. This was the hypothesis we did, so we targeted that. We got these results. If you remove the rheology additive and just use SCA, you get this graph, right? Now, if you look at this graph, it is very clear that if I use this paint, it's going to sag because it is the same as this paint, right? If I use this blue line and the recovery, it is almost this blue line over here. This hopefully has to be a good sample because that's what it's showing over here. Or if I use this, the green and it's going very high, just the SCA is going to be bad for flow leveling. That is what the graph denotes, right? So this is one of the ways we just try to analyze the sample. The second thing I told you, so you can see this comparison over here, Okay. So here is a little bit of advertising on our behalf also, because you're wondering how do we control those graphs, right? It is not so easy. You can just increase the SC up and down, and you can get the rheological curve. But if you have to fine-tune it in this way, if you really want to fine-tune it, and you want to get this sort of profiles over here, like this or here or this, you need the rheology additive. That's what I said, that only SCA if you change, you can get this part. You can get this going up and down. But if you want to adjust this curve over here and this rheology over here, you need those modifiers. Because if you don't do that, what I told you, you end up with this green line, just like this, and a very high recovery. Very good for sag, but very bad for flow leveling. So you look at the rheology modifiers, These are the rheology modifiers, we have in our toolkit. Like I told you, there are the CABs. Remember I told you, our CABs, unlike your traditional flow additives, they have a non-Newtonian flow. You see this, if you look at the solutions that you prepared, only this Solus 2615 is almost a Newtonian flow, right? But look at this is sort of, it has some flow over here. Look at these samples. So as you change the viscosity or the molecular weight of these samples, you get different rheology curves. The reason we have all these 5-6 options is because, this is our formulation. When you go to the suppliers, they have their own formulations. Their part A is totally different. Some of them may have very good sag properties. They may not need this aggressive rheology modifier. They may need just this or this over here. Some may have very weak part A. The SCA part may be very weak. They need very aggressive recovery. They may go for these samples. So the reason I'm showing this is, you have this variability. Because if you just pick up one SCA, then, you'll be forced to modify your part A. And many formulas don't like to do that, because part A is bulk of their formulation. They would like to use their protocols for the part A. So if you have got your own protocols, we don't want you to change your protocols to accommodate only one CAB from our side. That's why you have all these variabilities, right? Because depending on where you are on your journey with the SCA modifications, you have this flexibility now. You can play with the CABs, you can try this, and you can target this desired curves which we showed over here. You can target this profile, how you have to modify it. So this was about the rheology, right? Second thing we spoke about shear stress or yield stress. So, we are talking of gravity, right? You are just pouring paint on the vertical panel and it's just flowing down. It will flow down because of gravity. That is a gravity stress. Yield stress is when I'm forcing the paint to stay there, but I told you it has to flow also, because if it just stays there, it will not have any appearance. It has to flow also. So you have to put some pressure for it to flow. You need a minimum stress to make it flow, but that flow should not be very high, because if the flow is very high, then it will overcome the gravity and start dripping. So you can measure that. So that's what we did. The 3 samples that I showed you here, we measured them. So we measured the gravity stress of those 3 samples. We measured the yield stress. So the gravity stress is the stress that is required for it just to flow down by gravity, right? This is the minimum force it is required to make it flow, minimum stress. So now you look at these 3 samples, right? The initial sample. Here, the gravity stress is higher than the yield stress. So, what does it mean? It's good for flow, but it's going to sag because the gravity is going to force it to come down in this experiment. Look at this experiment, the optimized experiment. The gravity stress and the yield stress is almost comparable. So this could be potentially good for flow leveling. Potentially this has a good result, right? Look at the third case. When you remove the rheology additive, look at this. The yield stress is very, very high, 0.83. So what does it mean that it's going to be good for sag but bad for flow? So this was the analytical way we try to do it. But then now let's look at the real results. What do they do? So this is the real results. Like if you see this, if you see this experiments, remember the optimized paint. So this was the first trial, right, which was very bad. This was the thixotropy index over there on the lower side, right? We raised the thixotropy index to this because I told you the learning that we got from the lab to the applicator was, pro applicator was that the rheology has to be the same. It's just that you need to increase the bar because that lab was operating at a very, very high application parameters. So we raised the bar. From here, we raised the bar to over here, right? And then, I showed you the measurements also of the yield stress and all that, right? So look at this. This was a trial one where, this was the result on the pro. As we did this, look at the vertical from here to here. So this is a 90-degree vertical panel, and, you can see there's a good flow leveling here. The only issue that we ended up over here was, I know you can't see this panels very clearly, but on the horizontals, what happened was, because we arrested the sag over here so nicely, we got what is called as striping or barcodes. There are very fine lines. You can almost see it over here because the horizontal has to be perfectly smooth, right? So this is the current status where we are, that, with these modifications, we are able to improve this, sagging from here to here. We are having a barcode over issues over here right now. So what are we targeting now? Next is, like I told you, we need to overcome this because we need to have a common paint that can work for both the horizontals and verticals. We already have a vertical solution. We have separate different one horizontal solutions, right? We need to optimize the two and get the best possible blend of where you won't get a barcoding or striping, but you won't get any sagging also. So that is something we have planned. We are working with next month to those trials, and then we are looking at partnering with other applicators also, because when we started this journey with Dur, and when we spoke to the other applicators, we realized that they have a different principle of their machine, not exactly like Dur. So the operating principle is different. So obviously this paint will not behave the same way that it behaved on the Dur applicator. But what will happen is the learnings that we captured over here. This rheology curve, this yield stress, this will surely be applicable because this is science. You have to match this. If your paint is going to have higher gravity than your yield, it's going to sag, that's for sure. You have to get this sort of things, right? So even if the applicator changes, ultimately when you formulate that paint, you have to match this. You have to come close over here. You can't be here, you can't be here because you'll go to the extreme ends. You have to have this rheology curve. Maybe the rheology curve for the other applicator may be here, maybe it may be here, but you have to have this curve. So the analytical techniques that we captured over here, the way we can use a rheology modifier to fine-tune this graph or this curve, or even play with the yield stress, that will surely help because, I believe all the applicators will be same, zero overspray. It's just that the pressure or the flow rates or the knobs that they have for controlling will vary. But the basic principle will be same. So you are going to have this. That's so, like I told you, we have developed a solution, we have come very close, it's not perfect. So we are trying to optimize a paint that can meet the horizontal and vertical together, because that's the ask given to us. But like I told you, the intention over here is to walk you through the process that just SCA is not good enough. You need a rheology flow additive, a flow additive of this nature, because that is very important. This nature. If you use a traditional flow additives, it will be like this. So what will happen is they'll flow nicely, but if there is no recovery, when the shear is removed, you may end up with sagging. So you have to have this recovery. The moment the shear is taken away, the paint should recover. I know I went through pretty quickly, but hopefully it'll give you some idea about what this application is about, how we can do it, or what are the knobs to tune it. Because it's very early stages, But like I told you, if you can do this on an automotive line, because today you saw that in the morning, right? The Chevrolet cars, they have those bands, they have the stripes, or you saw that Charleston vehicle, right? When they went for the two-tone finish on that, they had a new lease of life. If you try to do that in a conventional process, because you heard that, right? If you try to do that in a conventional process, you will be losing minimum 2 to 5 cars production, depending on how much customization you are trying. If you have simple two-tone banding, maybe 1 car production. But if it's like the Charleston or the one that you had on the Chevrolet, on the bonnet, on the roof, on the sides, it will be minimum 2 to 3 cars. So every time you do that in a conventional spray, you are going to lose 3-4 cars production. It's a very manual consuming process. When you go with this, it opens up, it changes the whole equation. You can do this in an automatic way. You can do all that customization that you want, and you don't lose any productivity. So, this is a future. We believe in it, and I know it's at the early stages, but the faster we can do this, the faster we can implement. Customization is something that can be done very easily. I know there is a project, where I won't tell the name, but there is other company who's working on an advanced digital application. Literally, with that application, you can print a picture on the car body. Now with this, you can do a two-tone or, clip art sort of images. With those applicators, you can really paint pictures, maybe a family portrait on the car body in the future. But that is what is happening over here. That was all I just want to say. That.
Couple of questions here on the app. The first one is, did the formulation that worked the best have a gravity yield stress ratio close to 1? And is that meaningful or a coincidence?
No, if you just measure the gravity stress on its own, it's not meaningful. You have to measure the gravity stress of the paint along with the yield stress. Because I told you, gravity will just tell you that, is it going to flow down or not with the gravity, but on its own, it has got no relevance. Because I told you have to have the flow also, right? So you have to have some yield for the paint to flow. That yield stress and the gravity stress has to be measured together. Because that equation, remember, this equation. Because if you just measure this in isolation and you don't measure this, you just can't infer from that. If it is 1, it's going to be sag very badly, or if it is 0.2, it's going to be very good. Like I told you, you may think 0.2 is very good, right? But 0.2 comparison to what? 0.2 in comparison to this. The stress, the minimum stress is required for your paint to flow, because you want the paint to flow also. If you're doing your base coat, forget all this. You don't need all this. Because you don't want the flow from base coat. The clear coat is going to take off the flow leveling. But if you're doing this application, you need to do both together. Your gravity stress has to be more or less close to the yield stress. Not very high, not very low.
Okay, next question. How did you select the dry film target film bill range?
No, we went by the OEM specs, because like I told you, when you started the project, and when they explained to us that they want a single coat, you should not wrap, because you realize, right, this is almost like a shower head. You are just pouring paint, not atomizing it, and you want the paint to stick over there. So we thought, okay, maybe they may be just looking for 5 microns or 10 microns. Because I told you, if it is zinc, you can do that very easily. But the OEMs are very clear. They said, no, we want minimum 30 on the verticals, minimum. And 40, because this is, you are going to do this in an OEM line. So when you get a car from an OEM line, you're going to expect the same specifications. When you do it in the garage, or you're putting stickers or decals to do all this, you don't expect that, right? Because they're going to last for 6 months or maybe 1 year. But if an OEM is going to commit this, then they're going to expect that this car is going to have the same finish, the same appearance, the same durability of the original car that you're buying. And so the specification was minimum 30 for the verticals, minimum 40 for the horizontals.
Okay. How did you measure the gravity test and yield stress of the paint? Using a rheometer?
So that is a little bit proprietary. When we have one-on-one discussions, we'll surely share with you. But partially answer is correct, rheometer.
Is there a way to select an RCA based upon observed performance in the EcoJet Pro process or with yield stress data?
Yeah, because I told you they both go in hand. If you see this, I remember when you have to, if you just use SCA, what happens is, if you just use SCA alone, what will happen is, we'll end up with this sort of graph. Remember this green line? This is pure SCA. And if you sort of get this is almost like, this red line. It's very good for sag, no doubt about it, but it's going to be very bad for flow. Now, if you are, so depending on where you are in your journey, if you are very high like this, then, you need a rheology modifier, which is going to be almost like, you need to commit here somewhere, here in this range. But suppose, you are already here in your formulation, the part A, where you are using your SCA, and you are already here somewhere, and you just want to fine tune it, then maybe you don't need such an aggressive, you just need to go to this, one of these rheology modifiers. But if you are way down and you really want to take it high, then you may have to go here, this sort of rheology modifiers. So you need to quantify that. You need to measure where you are first for your rheology. Once you know where you are in the rheology, the second thing what we say is that, after you do that, then measure this. Measure your gravity stress and yield stress. Because, this will give you a good idea that, if your gravity stress is very high, you are very strong on the SCA part of it. You need to then bring it down to make it flow. Because your stress, the yield stress which is required for it to flow is so high that it's not going to really give you a secondary flow. It's going to give you orange peel. So after you do the graph plotting, check this. And then that will tell you where you are. Because I told you, if this is very high, you need a really strong, aggressive RCA to bring it to this level. But if you are like, suppose for argument's sake, you are here at 0.4 over here, then you don't need a very strong RCA agent. Then you can use a medium RCA agent to bring it close to this.
Okay, we have a couple more questions. How is the hot box stability of the Monocoat with these SCA and RCA modified formula?
What is that, high?
How is the hot box?
Hot
How
box?
is the hot box stability of the Monocoat with these SCA and RCA modified formula?
Oh, so I did not understand hot box. Heat stability. Okay, no. So that we had done it because, like I told you, when we designed this formulation, it was with the automotive OEM protocols. I just showed 2 ingredients of the formulations, but that they are not the only ingredients. So we are ensured that the pigment that is used over here, the other ingredients that are used over here, they already meet the automotive protocols. So it's like, so the formulation, we are going to test it obviously because, we don't want to start testing all these 32 formulations over here. But this formulation which is over here now, the formulation number 2, is already designed as per the protocol. So we are testing it. Obviously, we are testing for weathering and everything. But we don't believe this is going to be abnormal because, like I told you, I came from the coating industry. I spent 23 years in the coating industry before moving here. So when we made this paint, we are ensured that we are in those protocols. We are not broken those protocols of a formulating OEM formulation protocols. So it should pass, technically speaking.
Okay, and our last question, do you have some ideas on how to improve the barcoding?
That is what we are also doing now, next trial. So, because if you see, we got a paint that is working very good on horizontals, okay? We got a paint which is working very good on verticals now, but unfortunately it had a barcoding. So we already have 2 paints. Technically, we can go to the customer and say right now, okay, if you want 2 paints, this is your horizontal paint, this is a vertical paint. But like I told you, when customers are very clear, they want a single paint to do both the jobs. So one of the ways we are trying to do is, this is going to be somewhere here. The sweet spot is going to be here somewhere. But so we'll be taking these 2 paints and we'll be trying mixing and matching them. Is one of the ways to do that because it's going to come to a blend of that horizontal paint that we have and the vertical paint that we have. What is the sweet spot? Where we mix the 2 together, that it takes care of barcoding as well as sagging. Second thing, what I have not shown over here is we are trying to understand this, is this barcoding really related to this yield stress or gravimetric stress? Because, this paint is not atomizing, right? So we are measuring the surface contact angles also because what happens is maybe this requires a surface tension improvement and so it just flows away because that barcoding is like what you see on the box, that's why they call it barcoding. Maybe you really don't need an RC or SC over there. Maybe you just need a traditional silicon-based surface additive to reduce the contact angle so the paint flows out. So we are trying those options. One is, reduce the surface tension and see whether it flows in the existing paint itself, this paint itself, or use a blend of the one we had for good horizontals, the one we have for these verticals, and see if there is a spot, where both at a particular ratio you get the desired results. Obviously, the bell parameters also are going to vary because here we are doing everything in a single coat, right? And we are trying to do this, and we are operating at a very high velocity right now, the maximum tip speed. But if you reduce the tip speed or if you change the solvent balancing, try to make it slow, you may still have that slight barcoding away. So there is a solvent balancing, there is a machine parameter balancing, there is a surface tension contact angle balancing, or just blending the two paints and seeing if there is a sweet spot. So that is what we are targeting now in the Q2.
Okay, thank you very much.
Yeah.
Appreciate it.